All right, on to the chapter 4 problems. The first one was 13. This is a little less math in this problem, so it's going to be pretty short. So classic. The trick here is classic Ethernet. Oh, let's get the question. So, what's the baud rate of 10 megabit per second classic Ethernet? So, recognize that if it's 10 megabyte or 10 meg per second is the data rate for Ethernet. The trick here is just recognizing that classic Ethernet uses Manchester encoding. And since Manchester encoding has 2 signal periods per bit sent, the baud rate is simply twice the data rate. So if it's 10 megabits per second, then it uses Manchester encoding, so it's 2 signal periods, then it is 20 megabyte. All right, on to number 15. I know we talked about this in class a little bit, but the question in 15 is you have a 1 kilometer long 10 megabit per second carrier sense multiple access collision delay CSMA CD, so collision detection lands, not 802.3. Just trying to make it more simple there for you. And has a propagation speed of 200 meters per microsecond. So the repeater's not allowed in the system, which means that we don't have anything screwing it up there. And data frames are 256 bit long, including 32 bits of header, checksum, and overhead. The first bit slot after successful transmission is reserved for the receiver to capture the channel in order to send a 32-bit acknowledgement frame. What is the effective data rate, excluding overhead, assuming there are no collisions? Wow, that seems like a lot. But let's write down what we actually have in this thing and see where that gets us. So, the first thing is we have a 1 kilometer long cable. Right? The baud rate or the data rate is 10 megabits per second. Right? That's what the physical cable can handle, or the physical layer can handle. Doesn't mean that there's the effective data rate's the same, right? And our propagation is 200 meters per microsecond, right? So, what is if that's the propagation speed, what's the propagation delay? Well, it's 200 meters per microsecond. We have to go a kilometer. So the propagation delay from A to B, so not round trip, is 5 microseconds. And that means that the round trip propagation delay and the round trip delay is twice that, 10 microseconds. And then we just need to figure out some other things. So the question is, how long does it take to send, if you're filling up the line at this particular data rate, your 256-bit frame. So if the 256-bit frame, they're making this easy numbers right for you, it takes a frame, this is to stuff it in the wire, takes 25.6 microseconds. So, and then the acknowledgement, which is a 32-bit acknowledgement frame. So the ACK takes a 3.2 microseconds. Whatever. So now it just becomes a summation. We're going to send this one frame, and you're going to get an ACK out of it. So what do you have to do? Well, it is a summation problem. So the first thing you have to do is you have to transmit, you have to seize the line. And then you have to transmit data. And then that's this amount of time it takes to get in there. But also remember that it takes 25.6 microseconds to stuff the line, but the data has to get to all the way to the other side first, right? So then you have like we'll just call this like the last bit. And so that is the time it takes for the last bit after this 25.6 seconds of stuffing it arrives at the other side. And that's simply the propagation delay, right? And then the receiver has to seize line. And it has to send the ACK, right? So send the ACK. And then the last bit has to get there to that one, right? And so now you have this summation problem, right? So how long does it take to seize the line? Well, in order to seize the line, you have to transmit, and you have to wait the time it takes to reach the other side, plus you have to wait because somebody could start transmitting at the moment or the instant, I guess, before your data hits, right? So you need to wait the round trip delay here. So that is 10 microseconds. And then to transmit the data is 25.6. And then the last bit is 5. And then to seize a line is another 10 milliseconds. And then it's 3.2 for the ACK. And the last bit is, again, 5 microseconds. If you sum all this up, you get 58.8 microseconds. And in this period, how much data was actually sent? Well, this actually comes in to the 32 bits of header, checksum, and other overhead. So the data sent was actually not 256 because we had a header that they actually told you about in there. In that, so the data actually sent was 224 bits, and it was set in this amount of time. If you take that and put it into seconds, it is 3.8 megabits per second. All right. So, in this particular question, this is actually another simple one. It's an IP packet to be transmitted by Ethernet is 60 bytes long, including all of its headers. If LLC is not in use, is padding needed in the Ethernet frame? If so, how many bytes? So, the numbers that you get out of this thing are a 60 byte IP packet. So the only real knowledge other than you need out of this, other than generally how the whole layering works, is Ethernet. And so with Ethernet, what is the minimum packet size? Well, the minimum packet size for Ethernet is 64 bytes. So the question is, does a 64 byte IP packet or 60 byte IP packet need padded 4 bytes to meet the minimum requirements for Ethernet? The answer is no, it doesn't, because remember, in layering, you have right, we're taking something from the network layer, which is 60 bytes, and we're putting it into Ethernet, which has a minimum of 64. The problem is it makes you think that you need to pad this thing, but remember, when we drop the layer, this 60 byte IP packet right here is going to have to go into Ethernet, and Ethernet is going to encapsulate it. And when it encapsulates it, if you look at the what's needed to do there, the encapsulation has 18 bytes. And so since it has 18 bytes, when it gets passed down and Ethernet actually wraps this thing around, it's actually not 60 bytes anymore, it's 78. And since it's 78 bytes, it meets the minimum frame length of 64. So it doesn't need any padding at all. All right, this is question 18. Question 18 simply just understands why. All you need to have is the actual understanding of why a frame size is what it is. And the question states, Ethernet frames must be at least 64 bytes to ensure that the transmitter is still going in the event of a collision at the far side of the cable, right? In other words, the minimum size has to be the full length of the cable. Fast Ethernet has the same 64 byte minimum size, but can get its data bits out 10 times faster. How is this possible to maintain the same minimum frame size? Well, in regular Ethernet, it's 64 bytes because that's when it fills the cable up. That means that the cable actually is full of data. Now, in fast Ethernet, you want to have the same frame size for other reasons, interoperability reasons. And so, if you're pushing the data into the cable at 10 times the speed, how can the frame size remain the same? And a simple answer here is that it remains the same because you simply change the wire delay in fast Ethernet to 1/10 the size, because you 10 times the data rate, you have to have 1/10 the wire delay.